Let's now turn our attention to portfolio returns and variance and see if we can slowly link portfolio returns and variances to matrix algebra. Here we have the formulas for calculating expected returns and risk in the two-asset case. The formula for expected returns is just a weighted average. Calculate the weights times by the expected returns for each stock. And we know that the weights must add up to 1. Let's turn our attention to the formula for portfolio variance. We can simplify this formula, or rather rewrite it. So sigma squared P is equal to W squared A times by sigma squared A plus W squared B times by sigma squared B plus, well, let's gather all the terms that are similar. So 2WA WB sigma A sigma B times by rho AB. And remember that rho is the correlation between asset A and asset B. We can actually simplify this still further. How? Well, the covariance between asset A and asset B is equal to the standard deviation on asset A times by the standard deviation on asset B times by the correlation between asset A and asset B. More formally, if you want to calculate covariance, what you'll do is calculate the expected value of the returns on stock A minus the mean for stock A multiplied by the returns on stock B minus the mean returns for stock B. Notice that the formula for covariance here, sigma A times by sigma B times by rho AB, is also up here in our expression for portfolio variance. We can substitute in then. So we get WA squared times by sigma squared A plus WB squared times by sigma B squared plus 2 times by WA times by WB times by the covariance between A and B. We're going to use this adjustment and propose a new general formula. First, we need to change our notation. Let's denote the variance of returns on an asset as being sigma AA for asset A or sigma BB for asset B. The covariance between asset A and asset B will be denoted sigma AB. Now let's look at our formula for returns. Our formula for returns is just the sum of the weights times by the returns. That's what we saw in the previous slide. Here we've got this summation between stock I equals 1 to M. M is equal to the total number of stocks in the portfolio. So we've generalized the formula. We also have the formula for portfolio variance, which is equal to the sum of WI squared times by sigma II. This is the variance component here. And then we have our covariance component, which is going to be equal to 2 times the double summation of WI, WJ times by the covariance between stock I and stock J. And this formula for variance can be simplified to this expression we see at the bottom of the page. You may not believe that this formula for variance gets simplified to the final formula we see. The easiest way to see that this formula works is to consider the two-asset case. Let's apply these formulae to the two-asset case. First of all, let's consider portfolio returns, which are going to be equal to the summation from I equals 1 to 2. I'm going to be summing up Wi times by Ri. If I equals 1, we get W1 times by the returns on asset 1 plus, it's a summation, so we're doing plus, suppose I equals 2, then we get W2 times by R2. That's what we'd expect. Now let's think about portfolio variance. And we know that we've got the summation from I equals 1 to 2, and the summation from j equals 1 to 2, Wi, Wj, sigma ij. Suppose I equals 1 and j equals 1, what do we get? Let's plug in the numbers. We get W1 times by W1 times by sigma 1, 1. And because it's a summation, we're going to do plus. Suppose we set j equal to 2. We're going to now get W1, W2, sigma 1, 2. Now we can set I equal to 2 and reset j equal to 1. We get W2, W1, sigma 2, 1, plus, now let's set j equal to 2 as well. We get W2, W2, sigma 2, 2. We can simplify this formula. Remember that the covariance between asset 1 and asset 2 is equal to the covariance between asset 2 and asset 1. They're the same thing. So let's simplify. We get W1 squared, sigma 1, 1, plus 2 times by W1, W2, sigma 1, 2. These two terms can be combined, plus W2 squared, sigma 2, 2, which equals W1 squared, sigma 1, 1, plus W2 squared, sigma 2, 2, plus 2 W1, W2, sigma 1, 2. This is the formula we've seen before for the two-asset case. So the formulas proposed on the previous slide are correct. What we're going to try and do now is extend those formulas into matrix algebra. For expected returns, here we see the formula that we've just introduced. It can be rewritten in matrix notation as W transpose times by mu. And here, W would be equal to a column vector with WA, WB, if we're thinking about the two-asset case. And mu would also be equal to a column vector, and we'd have the expected returns for asset A and the expected returns for asset B. We can also convert our formula for portfolio variance into matrix algebra. It's going to be equal to W transpose times by S, and S is called the variance covariance matrix. So we do W transpose times by S times by W. The variance covariance matrix S takes the following form. It's going to be a 2 by 2 matrix if we're looking at two assets. It's going to be sigma AA, sigma AB, sigma AB, and then sigma BB. What you'll see is that the diagonal terms are equal to the variances for each asset. So we could label up the assets along here, A and B, A and B. And you can see that the off-diagonal terms are the covariances and the diagonal terms are the variances. To convince yourselves that these matrix algebra formulas work, the thing to do is to write out the formulas and test them. And we'll do that for the two-asset case. We know that the expected returns on the portfolio are equal to W transpose times by mu. We know that W is equal to, the matrix W is equal to WA, WB. We know that mu is also a column vector with the expected returns for each stock, A and B. We also know that S is the variance covariance matrix, and that's equal to sigma AA, sigma AB, sigma AB, sigma BB. Let's calculate our expected portfolio returns. It's going to be equal to W transpose. If we transpose W, we get a row vector, which is going to be WA, WB, times by mu, which is the expected returns on A and the expected returns on B. Can we do this matrix multiplication? We can. Look at the dimensions. W transpose is a 1 by 2 and mu is a 2 by 1. So the number of columns in the first matrix matches the number of rows in the second matrix. The result of this matrix multiplication is going to be a 1 by 1 matrix. You can see that here, which is what we want. We want the expected returns. It should be a 1 by 1 matrix. If we do this matrix multiplication, we're going to multiply the weight on asset A times by the expected returns on asset A plus the weights on asset B times by the returns on asset B. We get WA times by the expected returns on A plus WB times by the expected returns on B. That's exactly the formula we've seen before. What about the portfolio variance, which is equal to W transpose times by S, the variance covariance matrix, times by W? Can we do this matrix multiplication? Well, we know that W transpose is 1 by 2 times by S, which is a 2 by 2, times by W, which is a 2 by 1 matrix. Let's consider W transpose times by S first. We can do that matrix multiplication. What about S times by W? We can do that matrix multiplication as well. The result is going to be a 1 by 1 again, which is exactly what we'd hoped for. The portfolio variance should be a 1 by 1. Let's write it out then. To do this multiplication, let's first consider multiplying W transpose times by S. That's going to give us a 1 by 2 matrix. How do we do this calculation? We're going to do WA times by sigma AA plus WB times by sigma BB plus WB times by sigma AB. That's the first element. And then the second element will be WAA times by sigma AB plus WB times by sigma BB. Let's do this now. WA sigma AA plus WB sigma AB. That's the first element of the matrix, and then the second element is going to be WA sigma AB plus WB sigma BB. And this matrix is going to be multiplied by WA WB. We can do that multiplication now. We're going to get WA sigma AA plus WB sigma AB all multiplied. So we're going to get WA sigma AA plus WB sigma AB all multiplied by WA, and then we're going to add WA sigma AB plus WB sigma BB all multiplied by WB. We're going to get WA squared sigma AA plus WA WB sigma AB plus WB times by WA sigma AB plus WB squared sigma BB, which if we simplify this down, we get WA squared sigma AA plus WB squared sigma BB plus 2 WA WB sigma AB. That's the formula that we've seen before. That means that our formulas on the previous slide for portfolio variance and expected returns that use matrix algebra are correct. We'll be able to use them in Excel. The final thing we need to consider is the variance-covariance matrix S. How do we calculate the variance-covariance matrix? We know how to calculate variance. We know that variance is deviations from the mean, all squared. Then we divide through by the number of observations minus 1. The covariance calculation is actually very similar. We look at deviations from the mean for stock I multiplied by deviations from the mean for stock J, all divided through by m minus 1. The question is, how do we calculate variances and covariances efficiently, so in a quick way? We can use matrix algebra. Consider matrix A. Matrix A is a matrix of demeaned returns for all the stocks. Along the columns we have stocks. Along the rows, also down the rows, we have time. Column 1 is going to consider stock 1 across time. Column N will consider stock N across time. We can calculate the transpose of matrix A. That would mean we now have the stocks in each row, and in each column we'd have time. To calculate the variance-covariance matrix S, what we do is A transpose times by A, all divided by m minus 1. That's going to give us our variance-covariance matrix. But once again, it's very difficult to see that just by looking at these formulas. So let's work through an example. Matrix A is going to be equal to the returns on asset A at time 1 minus the mean. The next element will be the returns on asset A at time 2 minus the mean, all the way through so that we have the returns on asset A at time m minus the mean. The second column of matrix A will consider asset B at time 1 minus the mean, and this will also go through till we have observation M for asset B. There is our matrix A. Matrix A is an M by 2 matrix. A transpose times by A, so A transpose times by A is going to be equal to, we have RA time 1 minus the mean for A. We have that, we can fill out this transpose matrix. We have the same for B. The rows have become columns and the columns have become rows when we take the transpose. There's A transpose, all times by A, and we know what A is already. Let's do this calculation. Let's consider the first row of A transpose times by the first column of A. What do we get? This would be the first element of A transpose times by A. Now let's consider what we should put in to row 1, column 2 when we do our A transpose times by A. We're going to look at multiplying RA minus RA bar, all multiplied by, well, now we're looking at the second column, which is our asset B information. So we're going to have the summation, again, from I equals 1 to M, asset A at time I minus the average return for asset A, all multiplied by the returns on asset B at time I minus the mean return on asset B. If we move to row 2 of our big matrix, we can do similar calculations. We're going to get the sum from I equals 1 to M. We've got our B now, and that's all going to be multiplied by initially RA. And then finally we've got the last element of the matrix A transpose times by A. And this is going to be all about asset B. We've got RB at each time period minus the mean for B, all multiplied by RB in each time period minus the mean. S is just going to be equal to A transpose times by A divided by M minus 1. If we look at the first element, let's take the first element of A transpose times by A and see what we get if we divide through by M minus 1. We get 1 over M minus 1 multiplied by the sum from I equals 1 to M, RA I minus the mean for RA, all multiplied by our AI minus the mean returns on our A. This is our formula for variance. If we did the same for the second element, or for the second row, column 1, we'd find we've got the covariance between asset A and asset B. So our formula for the variance-covariance matrix works. S is equal to A transpose times by A, all divided by m minus 1. Don't panic too much about whether you can do these matrix multiplications on paper. We're going to be doing them in Excel, where it is a lot easier. All you have to remember is to check that it is possible to do the matrix multiplication. Once you've done that, Excel does all the calculations for you. So this video has been very heavy on the theory. In class, we're going to focus on applying this in Excel, and I think you'll see that things are considerably easier in Excel. See you in class.